Hi everyone. Lesson 17 is on counting, which is the basis for many probability problems. Counting. It's not quite as easy as it sounds, but we are going to count how many possible ways that things can happen. In part A, we talk about the fundamental counting rule, which drives much of this lesson. Let's say there are two decisions to be made, decision A and decision B. For example, let's say there are m possible choices for decision A. Let's say there are 3 possible shirt colors you can choose from. Let's say that there are n possible choices for decision B, regardless of how A is decided. So let's say that you have 5 choices of hat color. And let's say that your choice of hat color has nothing to do with your choice of shirt color. You don't care about fashion. Then there are m times n possible ways to decide both A and B. You have a total of 3 times 5 or 15 possible ways to choose a shirt color and a hat color. If you have more than 3 decisions to make, then you just multiply the corresponding numbers of choices. Now, it could be you who's making the decision, or it could be fate. So, in example 1, we're going to look at passwords. Assume that a password must have the following characteristics. We're going to find out how many possible passwords there are, how many valid passwords there are given these specifications. So the password must be exactly 4 characters long. It must begin with an uppercase letter that affects the first character, and each of the other characters can be an uppercase letter or a digit from 0 to 9. That affects these other 3 positions. Well, we can think of a big bushy possibility tree here. How many possibilities are there for the first character? Well, how many possible uppercase letters are there? There are 26 in the English language. Now for these other 3 positions, regardless of what happens here, how many possibilities are there for an uppercase letter or a digit? Well, there are 26 uppercase letters. There are 10 digits from 0 to 9. So we have a total of 36 possible characters for the second position, regardless of what happens in the other positions. For the third character, again, we have 36 possibilities, regardless of what happens elsewhere. For the fourth character, again, we have 36 possibilities, regardless of what happens elsewhere. Again, think of a big bushy tree with many branches. The total number of possibilities, the total number of 4-character passwords that are valid here will be 26 times 36 times 36 times 36, or about 1.2 million. What's a faster way of writing this? 26 times 36, what? 26 times 36 to the third. Very often we can use exponents or powers to write this as shorthand to show work, and you should show some work. If you give me a final answer that's wrong, how can I give you partial credit? Remember that on a calculator, the exponentiation should precede the multiplication. So 36 to the third comes first, and then you multiply by the 26. Okay, now this leads directly to a probability problem. Let's say that all possible passwords are equally likely, and you get a random one. We're assuming a uniform distribution among these 1.2 million plus passwords. What then is the probability that your randomly selected password will be I hate you? IH8U. What's the probability you get that by chance? Well, each of these are equally likely. The probability of you getting this, or any valid password, will be 1 over the 1.2 million or so. So that's why these counting problems can lead directly to probability problems.